Modern recycling is failing because it was never designed to restore material value. Let's begin with an uncomfortable truth. Most modern recycling systems are built around damage control, not restoration. Plastics are downcycled, tires are shredded. Waste is managed, not transformed. Meanwhile, millions of scrap tires sit in landfills or stockpiles, slowly degrading while policymakers talk about circular economies. Yet 80 years ago, under wartime pressure, chemists developed processes that treated rubber waste not as trash, but as a recoverable strategic resource. They didn't grind it and walk away. They chemically attacked it. They broke bonds. They reclaimed usable material. That history is largely absent from today's recycling conversation. This is not about nostalgia. It is about confronting whether modern industry abandoned viable chemical recovery methods because they were inconvenient, energy-intensive, or unprofitable in peacetime. If you are serious about industrial history and resource sovereignty, this matters. The chemistry of vulcanized rubber explains why tires seem impossible to recycle. To understand why modern recycling struggles, you have to understand vulcanization. Tires are not simple plastic. They are cross-linked polymer networks strengthened by sulfur bonds. These sulfur bridges create elasticity and durability, but they also lock the material into a thermoset structure. Unlike thermoplastics, vulcanized rubber cannot simply be melted and reshaped. Shredding tires into crumb rubber does not reverse this chemistry. It reduces size but preserves the cross-linked network. That is why crumb rubber is typically used as filler in asphalt or playground surfaces rather than transformed back into high-grade rubber products. The molecular structure remains intact and resistant. The 1940s salvage chemists understood this clearly. Their objective was not size reduction. It was a bond disruption. Wartime salvage operations used heat and pressure as industrial tools. During the 1940s rubber shortages, reclaim plants adopted high-pressure thermal processes, sometimes described as rubber cooking. Ground rubber was subjected to elevated temperatures in pressure vessels with controlled chemical environments. Alkaline solutions, oils, and mechanical shear were used to weaken sulfur crosslinks without destroying the entire polymer backbone. The principle was selective devulcanization. Heat alone can degrade rubber indiscriminately, producing low-value byproducts. But under controlled pressure and chemical conditions, crosslinks can be attacked preferentially. The result was reclaimed rubber that could be blended into new manufacturing batches. For viewers interested in practical application, the modern equivalent would not be a backyard experiment, but an engineered reactor system. High-pressure autoclaves already exist in industries ranging from food processing to composite manufacturing. With appropriate safety controls, similar vessels can be adapted for controlled devulcanization research. Reclaiming sovereign resources requires changing how we value waste. Scrap tires represent stored hydrocarbons, carbon black, steel reinforcement, and polymer chains. Calling them waste, honestly, just ignores their chemical value. During wartime, rubber scrap was treated as a national asset. Collection drives were organized not out of environmental concern, but, out of strategic necessity. That mindset shift is, absolutely critical. If you are involved in the local industry, one actionable step is to investigate how tire collection networks operate in your region. Many areas, in fact, export shredded material or just stockpile it indefinitely. Advocating for pilot reclaim facilities that focus on chemical recovery, rather than simple shredding, is a practical civic engagement strategy. From an engineering perspective, researchers can revisit archived salvage manuals and compare historical methods with modern catalytic systems. Advances in temperature control, emission capture, and solvent recovery actually make it possible to revisit these techniques under much stricter environmental standards. High-pressure thermal treatment differs fundamentally from modern pyrolysis. It is important to distinguish reclaim devulcanization from pyrolysis. Pyrolysis heats rubber in the absence of oxygen to break it down into oil, gas, and char. While useful, This approach destroys the polymer structure entirely. It converts rubber into fuel-like outputs rather than reusable rubber material. Selective devulcanization aims higher. It seeks to preserve the polymer backbone, so the reclaimed rubber retains mechanical properties. In practice, this means careful control of temperature and pressure to avoid over-degradation. Think of it as surgical chemistry rather than incineration. Modern research in supercritical fluids and controlled solvent swelling offers promising refinements to this approach. By swelling rubber networks before applying heat and pressure, bond accessibility improves. That reduces energy requirements and improves reclaim quality. Applying these lessons today requires discipline and serious safety standards. No responsible discussion of high-pressure chemical processing can ignore risk. Elevated temperatures and caustic chemicals demand strict containment, ventilation, and monitoring. Industrial reclaim operations must comply with environmental regulations and worker safety protocols. The lesson from the 1940s is not to replicate unsafe conditions. It is to recover the principle of targeted bond disruption. For professionals in materials science, an actionable path forward involves laboratory-scale devulcanization experiments using modern analytical tools. Techniques such as Fourier transform infrared spectroscopy and tensile testing can quantify bond breakage and mechanical recovery. Data-driven refinement can replace wartime trial and error. For survivalist-minded viewers, the takeaway is philosophical rather than chemical. Resource independence requires technical literacy. When systems fail or supply chains fracture, knowledge of material recovery becomes strategic. So, here's the thing, the real challenge is cultural, not technical. These days, modern recycling stories often put the spotlight on consumer responsibility, but honestly, industrial design mostly stays the same. You know, back in the day, historical salvage operations were actually systemic. Government, industry, and citizens all worked together around resource recovery. That kind of large-scale coordination is just missing today. If we start thinking of tires and complex polymers as reclaimable sovereign resources, it really forces a shift from passive disposal to active recovery. It also makes us rethink economic incentives, right? Sure, reclaim processes can be energy intensive, but then again, so is extracting virgin petroleum and making new polymers from scratch. For those of us who are seriously into history, this is the pattern that's actually worth studying. Crisis-driven innovation, more often than not, reveals capabilities that peacetime economics tend to bury. The past, honestly, offers some hard-earned lessons for a future that's going to demand real resilience. Modern recycling, well, it's not a total lie, but it's definitely incomplete. It manages waste, sure, but it doesn't really restore value. Back in the 1940s, rubber salvage chemistry showed that cross-linked polymers could be attacked, weakened, and reclaimed if you used controlled heat and pressure. The science was absolutely real. The plants actually operated. And the materials? They were reused. So, looking back at these methods isn't about romanticizing wartime austerity. It's about recognizing that material recovery, right down to the molecular level, actually has a precedent. As landfills keep growing and polymer waste piles up, selective devulcanization is something that really deserves a serious second look. If this dive into industrial history and material sovereignty struck a chord with you, go ahead and subscribe to the channel and share this discussion with other history buffs and folks who care about resilience. The answers to tomorrow's resource crisis might already be tucked away in yesterday's manuals, and we're absolutely committed to uncovering them.